Hey there, welcome back. We're going to talk now about IMFs or intermolecular forces. So I was talking a bit ago in the last video about bonds between molecules. That was more of a shorthand for what was happening because they're not quite bonds. It's more like the force that is holding them together. So there are three types of this force. There are H bonds, there are dipole-dipole bonds, and there are London dispersion forces. Let's talk about the H bonds, the dipole-dipoles first, specifically the dipole bonds. So, when you have a covalent bond, let's have an atom here and an atom here, they have polar ends. One end is positive, and the other end is negative because this one has all the electrons, and this end has no electrons. So it has slightly positive. Now, if you have two of these together, what is going to happen? Well, remember that opposites attract, so the negative side will actually pull itself towards the positive side, the one that has less, because opposites attract. And it's as simple as that. When they're different, the different ends are going to attract each other. And yeah, so the stronger in electronegativity one is, or the stronger the differences in an atom, the stronger this dipole-dipole thing is going to be. And it's just going to increase and increase and increase until it's as strong as just whatever. Now, there is a limit where it is so strong that we have to classify it as a different type. And this is called the H bond. It is the same concept of, oh my gosh, polar ends, except it's so strong that it's too strong. It can't be considered a dipole anymore and is very difficult to break. So an H bond is a bond made by hydrogen. So these are our dipole-dipoles. And there are, I think, only 3 instances where you can have a hydrogen bond. It's when the hydrogen is bonded to one of the 3 elements, fluorine, oxygen, or nitrogen. Now these, if you remember, are the 3 most electronegative elements, which I remember by Focln, O-C-L-N. The reason that is excluded from this is because chlorine is a period below, which means it's bigger, so it won't handle this. It has to be smaller elements. So hydrogen fluoride, hydrogen oxide, or dioxide, and hydrogen nitride are going to be the strongest things that form H bonds. So whenever you see an H and an F together within a compound, you can say, oh, that's where the hydrogen bonding is going to form. So let's see. I think in my notes I mentioned some other examples of this. Dipole H bonding. Yeah, so Focln, but minus the Cl. 3 most electronegative and small elements, we get extremely polar covalent bonds. It's as simple as that. So that's the basic concept of what it is. Now, what is a London dispersion force? First, I want to let you know that in terms of strength, the H bond is number 1. This is the really strong dipole-dipole. The second one is the dipole-dipole for when you have polar elements. You end up with elements that aren't really polar at all. But that's actually not where this force comes from. This is the force that is not dependent on polarity, and it's called the London dispersion force, or the van der Waals force. So London dispersion, or van der Waals. Okay. Now, the way this works, I would just compare it with gravity. Like, the bigger a compound is, the stronger the London force is going to be. So it's technically the one that can be the strongest out of all 3, but is by default the weakest, but is present in all compounds. For example, let's say I have H2O. So, like I mentioned, it's technically a dipole-dipole because if I have an oxygen and a hydrogen here, the polar ends are going to attract like the oxygen to hydrogen. Problem is, it's hydrogen, oxygen. Oxygen is really, really light and electronegative. So it's going to be too strong to be a dipole. Dipole, it's going to be an H bond. So the hydrogen and the oxygen are going to attract here. The hydrogen and oxygen are going to attract here. And that's essentially what's going to happen. And as you get more, it's going to be like, oh my gosh, the oxygen to the hydrogen, and this oxygen is going to have two hydrogens, and yeah, and that's how you form ice when they're all connected. Remember that if I start adding heat, these forces will start breaking apart and it'll separate. Um, but within a molecule, there is a force that is also applying to other ones, and that is the London dispersion force. So let's say I have molecule here, molecule here. They're kind of attracting each other just because, like, that's what the London dispersion force is. Um, as such, bigger molecules will have a bigger London dispersion force, so they'll attract each other even more strongly. And of course, really, really small ones don't really care. So that's why the London dispersion is the weakest, because when you have an element like H2O, uh, which is really, really small compared to a lot of other ones, it's only got like a weight of like 17 grams per mole. Uh, it's gonna be it's gonna be that. I'm lost. Yeah, it's gonna have like no magnitude of London dispersion force, even though the London dispersion force is there. So the question is, what does it matter that London dispersion exists? It matters when you get into really, really big elements, like ethanols. Ethanols are huge, just conglomerations of carbon and hydrogen and everything else. So they can be massive. And they will exhibit really strong IMFs in the form of London dispersion forces. They won't really experience these two because they're not very polar, but they will have that. Also important to note is that I mentioned in another video, but polar and non-polar dissolves non-polar. Let's get into that when you have substances. So erase this. Another note about the form of these London dispersion forces is that spherical molecules, even if they have the same mass, will not have the same London dispersion force as an elongated molecule. Like if you have your molecule in a chain formation, like I guess this, uh, where like every nexus and every end is like an oxygen or hydrogen or carbon, that's going to be way more powerful than just a conglomeration of stuff. So the longer and more elongated it is, the stronger the force is going to be. And of course, the less electronegative or polar it is, the more dominant the London dispersion will be, though really not by that much. The truth is, if an H bond is in the interaction, it's probably going to be the strongest one, and it takes the most effort to break up. Anyways, that's um, IMFs, I guess. Paramagnetism is just a basic concept where this actually goes back to a few units ago. I don't know why I didn't mention it. Maybe I did. When you have an element, oh, it's because paramagnetism is magnetism, which is kind of an IMF. Paramagnetism refers to a special type of magnetic field, which boils down to how many unpaired valence electrons do I have? So let's say I have a D shell, and it's going to have five orbitals. Um, Unpaired electron, unpaired electron, unpaired electron, unpaired electron. The more you have, the more paramagnetic it's going to be. Unpaired electron. And then at the point that it does that, it starts decreasing. I don't know why that is, but that's just kind of it. Anyways, the more unpaired electrons it has, the more paramagnetic it's going to be. Done. Let's see what's next on the IMFs. I feel like I'm missing something because I went fast. Oh yeah, the properties. This is probably the coolest part of it. So the strength of your IMF determines a few things. The properties of your substance. Um, Actually, first we need to talk about the states. So an IMF that is like charged with all its energy, uh, no, not charged, is in its most non-energetic form is going to be a solid. So when you have a solid, this is where all the intermolecular forces are playing against each other, all connected. But as you add energy, they start like getting riled up, and electrons start getting into the ghost shell, and they start getting excited and conductive, if you remember the band theory, and they start freaking out, and then the IMFs are like, well, peace. And so, as you add more energy, the IMFs break apart, and you get a liquid. Boom. And as you heat up a liquid, it will get eventually into a gas. At which point the IMFs are just done. They can't take it anymore. Uh, Now the strength of the IMF determines if it's gonna change between these states. That's how it matters. So the strength of an IMF determines its boiling point, its vapor pressure. I'm still not really sure what vapor pressure is. Um, it's going to determine its viscosity, and it's going to determine surface tension, which I feel like is like the same thing. Um, so, this is actually really cool because the higher, I mean, that's not why it's cool, but it's kind of just what I find cool. The boiling point, no, as the IMF gets stronger, the boiling point goes up, the viscosity goes up, and the surface tension goes up. Vapor pressure goes down. I don't know why. That's how it works. So as your IMF gets stronger, what it means is that the molecules are holding together more. So if you want them to break, you're going to have to pour more and more energy into them for it to do it. Uh, One thing to note is that when you change from a liquid to a gas, that is actually not a change in energy. Like the point of evaporation, or the boiling point, you could say, is just the amount of energy where that it reaches, where it's like, oh, I guess I'm a gas now. It is not saying, oh, I added some energy, so now you're a gas. It's like the threshold is not a change, but after that you can just keep adding it, and the gas gets a higher pressure. And it just keeps going like that. Uh, yeah, so boiling point goes up, vapor pressure goes down, viscosity goes up, surface tension goes up. Um, so water is an H bond, so it has a really strong whatever. It has a pretty high boiling point. I don't know about vapor pressure and surface tension relatively. You're going to be thinking, what? Water doesn't have that much viscosity. It flows really, really well, and surface tension as well. Like I can just break it, even though bugs can walk on it. But you're thinking relative into what you're used to. Think about oxygen. Have you ever seen liquid oxygen? It has to be really, really cold. Oxygen has very weak IMF because, ooh, my thumbnail is breaking. Oh my gosh, I lost it. Okay, anyways, oxygen has very weak IMFs because it is. Wait, what was the trend for the strength of an IMF? Was it size? Oh yeah, smaller ones. Smaller molecules have stronger IMFs. Yes. Yes. Where was I? Oh yeah, oxygen has an IMF like that. Uh, a weak IMF within itself, which explains why, in its natural O2 form, it is a gas. So if you think about it, O to O, 6 to 6 is going to be 12. So 1. So between them, they're not gonna hold together really well because there's no polar end. Like this end isn't polar and this end isn't polar either. They're both just what they are. It's neutral, which means that the molecules themselves aren't going to attract very well. And because it only has a mass of 30, uh, give or take a bit, molar mass of 30, give or take, O2 does, it's automatically going to have a really, really low boiling point because its IMFs are not strong at all. So it is naturally a gas. That is why certain compounds are naturally gases because their intermolecular forces are very, very low. And yeah, same goes for more. So this is when London dispersion forces really start to play. You'll be like, oh, that makes sense. Think about wax. Wax is a massive molecule with like 30 something carbons, 30 something hydrogens, 30 something oxygens. Like that's really, really big. Thus, that's why it flows. Since its IMF is so high, wait a minute, I'm confused now. Oh yeah, it's solid at room temperature. Like water is not solid at room temperature, but wax is. So you heat it. Have you ever seen like gaseous wax? Like, no, it's just it's so viscous at room temperature because if you want it to go any faster, you have to heat it up to a higher temperature. If that makes any sense, it's kind of like the opposite of oxygen. Same with like tar. It's a huge molecule, so it holds itself together way stronger than any H bond would within itself. So, so yeah. Anyways, think about it like this. Going in this direction is an increase in energy, uh, just generally as you go across the spectrum. So if you have a solid, you can say that that its IMFs. If you have a solid at the same temperature, you can say that the IMFs for the solid are stronger than the ones for the liquid. Uh, because at room temperature, that means the one that turned into a liquid has IMFs that are weaker because you put temperature in and then it started melting. Yeah, so it's essentially also melting point. It plays in with your IMFs like higher IMF, higher melting point. Metals have really, really strong or really, really high ones. Remember the when they were all just kind of connected? That's why they're so strong, or why they have such high points. It's because they're held together in that special way. Let me pause and review.